To introduce this talk, as you know, I usually do sharp introductions to the speakers. Yesterday, I even talked some Polish and got a lot of Twitter messages then. How can I speak Polish? Yes, and you know that Milen actually is also living in Poland. And he was saying, okay, what I'm gonna say to him now? What Polish word would I say that only he understands? With a lot of sh and so on and so on. But actually, I didn't sleep this night. I was thinking, how many Polish words else do I know? But actually, it's not about the Polish words. It's all about the stars that get together. You see, there are moments when all the stars on the sky stand like this. We got an awesome speaker. We got not only just an awesome speaker, but a speaker who was at the very first J Prime. Who was there, once again, at the first J Prime? Yes, not very many people, but you were there, so you saw him there. He actually came to support us for that first J Prime, and we are very, very happy that he is here, and this is another star for him. Once again, we have keyword Java. This is one more star for him. As I just understood, there will be live coding, which is 5 stars above for him. And of course, there is the AI, which is like tons of stars, because this is the buzzword. And once again, Milen will help us understand when are we going to lose our jobs. Milen,
hope not.
yes, Milen is really awesome friend of us. We are so much happy when he is here. So please warm welcome our great friend Milen.
Thanks, man. That's it. All right, thank you very much. Thanks, Jimmy. Yeah. Let me get up here so you can see me better. Not that I'm, pretty or something. All right, thank you. I didn't expect so many people, so it's amazing to see you all here. And before so after this introduction, I don't know what to say about myself. I guess I'm going to use a minute in a second. But before we start, just a little survey so I can kind of adjust the levels. Hey, raise your hand if you've done anything, any AI communication, anything with AI from a code. Okay, great. Keep your hands up if that was more than calling OpenAI API. Okay, so you folks are in the wrong room, because you already know everything I'm going to be talking about today. I don't know if you noticed, but the talk has like a little subtitle, beginner. So yes, we will talk about very, very basic stuff. So don't expect things to get overly complicated. First of all, because I'm not the machine learning, AI, whatever expert you used to on LinkedIn, even though I spent about 30 years working in software industry, working on all kinds of software for banks, insurances, telcos, you name it. But AI is relatively new to me as well, as it is probably for most of you. And when I say AI, let's be clear what we're talking about, because now everyone has different ideas. So no, we're not building Terminators here. Calm down. Super intelligence is somewhere else. No, we're not doing general intelligence. I mean, some people do claim we have it. I haven't seen it yet. What we're talking about is artificial narrow intelligence, meaning software programs being able to do some smart things, essentially, and not being able to figure out that a hand has 5 fingers. So that's the level of artificial intelligence we're talking here in this talk today. And then a little explanation of the why. So when I started dealing with AI and the whole hype, I was like, okay, I'm a Java developer. I've been doing this for many, many years, and I need to understand what's behind that. Calling a ChatGPT or OpenAI APIs it's calling an API. I mean, like, let's face it, it's an API. Whether there is a super intelligent AI behind it or something, dumb, it's calling an API. It's not, you don't really understand what happens behind the scenes. I need to understand what happens behind the scenes. Do I need to call an API? Can I run that thing locally and interact with it? So that was my motivation, to understand, okay, all this AI thing, what can I do with it from my Java code? And so I needed a mental model to start imagining how things are happening behind the scenes. And that's what I'm trying to give you today with this talk, and hopefully that's going to work. And as we talk about models, I want you to keep one thing in mind, namely that quote that says, all models are wrong, some are useful. Now, you may argue with that. I'll prove to you that's the case. Here is a model of the world. And that model is wrong. Now, you may not notice it immediately, but if you look carefully, you will realize that according to that model of the world, Greenland and Australia are the same size, which is wrong. So you have a completely wrong model of the world in technical terms, but it's still useful. It still tells you what's where the oceans, where you can travel, and things like that. So the fact that it's technically wrong does not prevent you from using that model in many, many circumstances. And so this is going to be the talk today. A lot of the things you'll hear will be technically wrong. So if the machine learning / data science inside you screams, that's wrong, yes, I know. Okay? I may not know what's the right one, but I know it's wrong. So, we talk about AI. Every time we talk about AI, you hear about AI, what you hear is models. AI models, model this, LLMs have the word model in it. So model. What is a model? So if you start digging, the first thing is that model is that piece of something that on one side you have this data scientists and machine learning experts, all the smartest people in the world with like the most expensive infrastructure in the world training it and producing it, and they do that great work and produce something, right? On the other hand is people like us who are talking or interacting with that model. And that's called inference most of the time. There are even companies who now build dedicated hardware for inference and whatnot. So it's this like two worlds. You either on the creating models side, or you are on the consuming, so to say, model side, which is not new thing, not a new concept in software engineering in general. And if you talk to Python developers, or not really Python developers, but people in data science field, for them that's very obvious thing. They don't even think about it. It's like, yeah, I just use throw some data and whatnot. But what is from Java perspective, what is that model thing that was bugging me when I started digging? I was like, okay. Started learning about it, and if you talk to the data science folks, they tell you it's a function. All right, so yeah, it's a function, you get some data, and it produces some data. And it seems like it's a fairly reasonable and sufficient explanation for all the data science folks. Okay, not for me. So I start digging more, and I find some comparisons. It's like, okay, let's try to make it look like code, right? So there is this function or procedure, depending on whatever language you use or call, and then you put some input data in it, and the body, the logic of the function is somehow generated and knows what to do, and then it produces some output. But then who generates the body of that function? It doesn't fit together to me. So the more I was thinking about it, like how to map that thing to things that I already know, it occurred to me that it's actually very similar to a piece of technology that pretty much every single developer has been using, which is databases. you essentially have a database, and you query, from inference perspective, you query that database with some piece of data, and you get some results back. And if you think about ChatGPT, for example, that's precisely the same concept, except that you don't use structured language, you don't use SQL, right, or whatever the particular database language is. You use natural language, but it's the same concept. You query it, and it gives you some results back. And then the reverse, like that's the inference part, and then the training part is basically filling that data, that database with data. Kind of like, database architects who figure out like what tables and schemas and indexes and keys should be there and whatnot. And so if you are on the consumer side, you don't really care about those things. So all the things that you care about is querying that database, getting the right data. But there are a bunch of folks who need to prepare that database so it works for you. And so came to this idea as like AI as a database model, and thought like, what if I try to simulate this just so that I can understand how that works? And so here is a tiny little demo. If you want to download it later on and play with it, not that there's much to play with, but that's the URL. Let me see if that's going to work now. Demo gods. OK, so I have a Postgres database running. And as you can see here, I have no tables at this database. So let's create some. So I'll open a file here, set up. And in here, I'm just going to create a table books. And I'm going to import some data from CSV file. And I'll create this extension vector. We'll talk about that later on. So let's run this. And if I refresh, there should be. OK, I guess it didn't run. Yeah, but OK. Let's do it manually then. OK, now it should be. Yeah, here you go. So there is a table, books, and it has some data in it. How to zoom in? Here. It has some titles and whatnot. And so now, what I would normally want to do with this, close that, is query. I want to now get some information. So ideally, I want to. I have a very simple table that has some information about some books, title and description. That's the entire thing. And so what I would want to do is give me the books that are about animals, or about music, or about I don't know, scientific achievements or whatever. But I can't do this with the regular databases because the only thing the database can do is match exact things. So all I can do is select something like this, and it's going to tell me, well, yeah, there is something that has the word music in it, right? But that's not all the books that have that are about music, right? So what we can do is we can use an extension to Postgres that is called text search, and allows you to do a full text search. Now, how full text search works is it has this thing called 2TS vector, and when you give it a text, it tokenizes it. Now, I'm pretty sure most of you are familiar with the concept of a tokenizer, so I'm not going to spend too much time on that. But it does some fancy tokenizing. So if I do this, you will see here that it converts the description into tokens. Right? Now, once we have the description as tokens, we can do fancy queries like this. And we can say, convert the token, the description to the token, to tokenize it, and then we can convert the query to a token and then search for the specific token. So if I run this, you will see here that's essentially a full text search. If you've done in the past. You can see here that it found the word piano and whatnot. So this is like much better, but it's still not what I want, right? It's still not answering the question. So next step is to optimize this. So now, instead of doing this live, we will create a table, and we will create a vector column in that table, and we will use something called embeddings in the future. You'll see that in a second. I forgot to create the previous table, I guess. Was rushing too much. Here we go, sorry. So here it is. So now to optimize this, because here, this query that I run, it does the conversion every time you execute the query. And so we now will create a table called books.ts. Let's do that. And we'll just update that table so that it has the TS description in the table. So let's look at these tables again so you know what I'm talking about. Refresh. Bear with me for 1 second. I promise you will get to the Java part. And here is the tokens column, which contains the tokenized version of the description. And now when we have this, we can now go to the vector part, and we can create a table that actually will contain another field called vector, and you'll see that why is that important in a second. Okay, so we have this table books vector now, and if I select from it, from the embeddings column, you will see that it all has null values, like no values in it at all. Now, what we will try to do is we'll come up with an idea to classify text. So we'll say, if a text is about animals, we'll put in the first column a value between a 0 and 1, which represents the percentage. It's like how much this is about animals. In a second, it will be how much it is about science, and in the third, it's going to be how much it is about music. And then we can do this for pretty much all the records that we currently have. And so this is what I call a naive tokenizer. So here is, no, that's not, where is my, here it is. Nope. IntelliJ, where are you? Here you go. So this is what I call naive embedding. So it's a piece of code that basically selects all the words from the database, tokenized, right, and converts them to this quote-unquote embeddings or vectors using this naive embedding thing. Naive embedding can generate embeddings. If you look into that code, it basically has 3 maps. And it basically says if it sees the word cat, dog, lion, bear, blah, 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 it applies a certain percentage, a certain probability that this piece of text is about animals. And it does the same thing for science, and it does the same thing for music. And it's like the super naive. So it creates a vector that has the size of 3, and the 3 elements of the vector represent, have some meaning, right? And so if you now, and then, let's hide that. And so then it goes through, selects all the records, all the rows in the table, and updates our vector accordingly to this naive embedding. So you will see vector update complete. And if I go back and do select again, now we have some vectors in here. So we know that this record has a 55%, this one, has a 55% chance of being about science. Like, super naive approach. So how can we make use of that? Well, we can now search. And this is a piece of code that uses the same table. And you can see it uses this TS vector to array kind of thing to convert. So we give our query a tokenizer, convert it to vectors, and then we find the vectors that are closest to our query. So this is what you will see here is you'll notice that the select doesn't have a where. We don't say, find me the records where this condition is whatever. We instead have something like order by distance. So basically, we're trying to find like the vectors that are closest to our vector. All right, I'll run this. I'll explain that on the slides in a second. I'll run this, and then you will see that it returns some books that are relevant to our query, and our query is somewhere here. I want to learn to play a song on the piano. This is what we ask. It converts it to vectors and then finds the nearest vectors and returns us the nearest vectors, and this is what we got. Now, what this means conceptually is that we are still in the three-dimensional space. We have three. The vector size is 3, so we for every piece for every record in the database, we can draw a vector in a three-dimensional space. Now our query comes in, so we tokenize the query, we convert it to a vector, and here is our query vector. Now what we can do is find what's called the nearest neighbors or similar vectors. Now, this is one way to do it. It's called Euclidean distance, which is basically the straight line between the edges, and you can this way find vectors which are close. There are other ways to do it. For example, here is an article that can tell you more about Euclidean distance, or you can do a dot product, which basically also takes the angle, or you can do a cosine similarity, which only takes the angle. If you want to dive deep into math and linear algebra and all that things, like there's plenty of resources out there to navigate. But essentially, what you're trying to do is you're trying to find the vectors who are closest to you, because that's the likelihood. Now, three-dimensional space is hardly enough. Like imagine that you want to classify by a lot more. Like what you would do, you can go 500, and then you assign a meaning to each value on that vector. It's like not a task that as a human you can and would want to do. But what you can do is you can just say, I have an n-dimensional vector. And that's n can be several hundred, it could be 1,000, it doesn't matter. And now, if you have lots and lots of data that you know that this piece of data is somehow similar to this piece of data, you can run a training algorithm on top of that data that assigns values to those places. And those are called weights, by the way. So now you create something that knows how to map a text, or it doesn't have to be a text, it could be a sound, it could be an image, it could be anything, to vectors. Right? You need a lot of data to train a model, but once you have it, it can do it for you. And this is what's called an embedding model. And embedding models are the simplest types of models that exist. That's their job. They get some unstructured data, and they convert it into vectors. That's all the things they do. And now, okay, now you know. You don't know what all the models are, but you know there is an embedding model. How is that thing distributed? How is that thing useful, right? Well, in lots of different ways, as it turns out. So for any model, actually, that's true. So there's tons of different ways to persist that and distribute it. And one that is getting, I guess, more popular recently is the Onyx one, the Open Neural Network Exchange, because it kind of pretends to be a standard. But by the time I'm saying this, it may be another one. And you will see the popular Python frameworks have their own, like PyTorch and TensorFlow. Goof is another one that's very popular because of Llama. So there are plenty of ways to distribute those models. And so what a model is essentially this data, this bunch of numbers, lots of numbers, we're talking about gigabytes, as well as the framework that knows how to deal with those numbers. And these frameworks are also different. So if you get a model on TensorFlow, probably not going to work with PyTorch and vice versa. So yeah. But in the Java world, turns out, there is a library. Hey, there's a library for that. And the library is called LangChain4J. And one interesting thing LangChain4J does, among other interesting things it does, is that it provides some models as jar files for you. So there is this embedding model called all-mini LM L6v2. It's a model, it's one of the many embedding models that the only thing it can do is get a piece of text and convert it to embeddings. And it's provided in this LangChain4J embeddings all blah, blah, blah jar file, right? And so all you got to do is put that jar file on the class path or in your Maven, whatever, Gradle thing, and then you can use it straight from your Java code as a class. Now, behind the scenes, that uses LangChain4J, which behind the scene uses the Onyx runtime environment, which is the only thing that understands what Onyx model is, right? But all that is abstracted for you. All you need to do is, just grab the model and run it. And so I'll show you how that actually works. So let me hide this. Actually, hide it like this. And first of all, I think I need to. Where is my? That's not what I want. That's what I want. I want to create another table here before I forgot. So I'm going to create this table of book embeddings. And as you can see again here, embeddings are, the embeddings column is empty. And now I can show you, not this one, this one. How to do model embeddings. So it's the same situation as before, except, what happened? Whew. Magic. Okay. It's the same code essentially. The only difference is now we have model embeddings instead of my dummy, naive embeddings. And if you look at the code here, it says return all mini LV blah blah blah. And if you look at the import statements, it comes from lang from J blah blah blah. So that's all I had to do as from Java, is just grab that model, right, and use it. And because it is an embedding model, what I can do with that model is call .embed. So they even prepared the right methods. So later on, you will see using an LLM, and the LLM will have a method chat, right? So they kind of prepared this stuff so you can interact with the model the way you are expected to interact with the model. So if I want to create the embeddings now, I'm just going to run that code the same way I did before. And it's going to take a little while. But meanwhile, we can go back to here and select from the embeddings table. And now what you can see here is we have tons and tons of numbers. All right, I think this embedding model, I think, is the size of 300 something or 600, the vector size. Not quite sure. I will be able to see that later on with the next example. But there are also embedding models that are much larger. Like you can have an embedding model that has like 2,000 or 4,000. The thing is, the larger is your model, the larger is the vector size, the more precise is the model, the more memory you need, right? So, okay, so this is the part where you create the embeddings. Now is the part where you search, which is what is called a semantic search. So now we're doing the same thing, except on a different table, on the one with the embeddings created by the model, and we are doing the very same thing. We do embeddings, the distance between the value in the embeddings in our query, and this here is the L2, I can't never pronounce that word, the distance. There are like different ways to do that. If you do the equal instead of the dash in the middle, I think that's L1 or something. You have to check the docs exactly what the spec is. But basically, this is like the most common used version for distance. So this calculates the distance between the vector in the database and the vector that is created from your query. Right? And so we'll run that code here and see what it will find. And it will see that it finds different things that it found before. Like, for example, it'll find Chopin, the man and his music. It has music with the brain in mind. I think he did or like choral experience. So now this is finding things that are more semantically relevant to our query than the thing that we were able to find based on our naive mapping before. Now, that's all good, but we still operate on a database. Now, databases, as you can see, Postgres even has provided pgvector, which is a vector sort of vector store, and this is partially what we're using here. If you want to do this on a very, very, very large scale, you need a proper vector database, and one such is Pinecone. So, well, am I already at? Let me, yeah. So, in this case, LangChain4J allows you to do part of their like a common API to talk to vector stores. So here is an embedding store that connects to Pinecone through some, you need an API key, and you need to tell which region it works. And then it does the same thing. It selects title and description from books. And then it goes and creates the embeddings in batches of 500, because this is now doing it online. So let me find that. Make sure this works, as I'm not sure which. Okay. So as you can see here, I only have one index. And if I run the code now, it should create an index, connect, and upload all the vectors in the vector database. In batches. Yes, that was expected. And I'll explain to you why it happens after it works okay the next time. Or it doesn't. Let me see. Well, it created the index, so I'm clearly authenticated. And let me open it. Yeah, records count. Okay, so I'll explain to you why it happens after it works the third time. Here he goes. There is a bug in LangChain4J because what happens is when you create an index on Pinecone, it's asynchronous. So when the call returns, it tells you OK, but the index is not created. It takes a little while to create the index. The LangChain, however, tries to insert immediately after that, and this is where you get the unauthenticated message because the index is not there. So you have to wait a little bit for the index to be created before you can add stuff to it. So now, here is this, and as you can see, we already in this index I have like 1,000 vectors. You can see here like what is the text segment that was embedded and the ID, and you can see the actual vector here. And so you can use that now with billions and billions of vectors to search, which is what I'm going to show you next. Is basically the same thing. We have, I want to learn to play a song on a piano query, and it uses embedding search result here in query embeddings, and it gets the max results of 5. So if I run this, it's gonna now not query my Postgres database, but it's gonna query the Pinecone index, and it's gonna give me the results now from there. So, not this one. I'm lost on my own presentation. Yeah. So this was the embedding store. So we were talking all the time about embedding, converting text and stuff to numbers, which is boring because you've probably been using things like ChatGPT and Midjourney and whatnot. I was like, I want to use those things. Well, those things are more or less the same, except they require more and more resources. Now, so the difference between, like, conceptually, remember, all models are wrong, some are useful. Conceptually, what happens with this generator models is the same thing that happens with embeddings. They get similar things, and then they predict what is the next similar thing. Like, once they predict the next similar thing, they get the whole thing and predicts the next similar thing, and then predict the next similar thing. And this is like conceptually how large language models work when you interact with them. They just give you one token at a time. All right? And of course, technically, that's more complicated. You're probably going to have to go and read the paper about attention is all you need and about transformers and whatnot. But conceptually, it's the same thing. It just generates you the next token up until reasoning models, which is completely different story. But if you want to run them, basically, if you want to use a model like this, a generative AI, you basically have two options. You either call an API that the model is hosted somewhere on some infrastructure that can handle it, right? And you just interact through an API, or you run it on your local machine. Now, obviously, you need to have a machine that can run it. And this is one way to do it with Java through another tool called JLlama. Now, JLlama is a new kit on the block that can run a large language model. It uses the newest Java Vector API behind the hood, so it only works with the latest version of Java, and you have to provide some enable things for it to work, but it works. It's super slow, but it works. So let me sorry, that was funny, I guess. Okay. The reason I'm saying it's super slow is because it's terrible for when you do live coding and on stage, right? So this is the entire code. Like that's the whole thing. You basically say JLlama chat model builder. You give it which model you want to run. This is Tiny Llama, one of the smallest LLMs that you can run. right? And you can say build, and then you can say model generate, and it gets you the response. And that's it. That's the entire thing. The only bad thing about it is when I click that button, yeah, I now need to find the configuration where it actually has the settings for the vector API. The only bad thing about it is that when I run this code, I need to figure out what to do on the stage for a minute, right? Because it takes about a minute for that thing to spin up a model and then interact with that model and then get the result back. So as you can see here, it tells you that it's allocating memory, 27 prompt tokens. So that thing I want to learn to play a song on a piano resulted in 27 tokens. That's essentially what it tells you. And then it's allocating more memory. And thanks God I have a CPU with a GPU that can do this, because on my previous Mac, which had an Intel processor, that doesn't work at all. Like, you can't even run it. On this one you can. As I said, the downside is figure out what to talk about for a minute before it results in something. Hey, here you go. But finally, I'm talking to an LLM. And an LLM tells me, I asked the LLM that I told the LLM I want to learn to play a song on the piano, and it tells me to learn to play blah, 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 some answer, whatever. Now, obviously, that's not the most efficient way to do this. Another way to do this on a local machine is to use something called Llama. Now, Llama, you can think of Llama as a Docker for models, right? And Llama has its own repository. You can do stuff with Llama, like, where is my so Llama list, and you will see what models I have installed on this machine. So it's Cogito, Gamma 3, Qwen, Llama 3.2, and DeepSeek Coder, right? And if I do Llama PS, you can see no model is currently running on my machine, right? But I'm going to go back now to my code. And here is the entire code as well. Again, using LangChain4J. So it's the same query, and I'm saying I want to use Llama 3.2. And this is going to be a Llama model running on localhost, blah, blah, blah. Because I already have, you can see here, I already have a Llama running on my machine. It's just that when you don't need a model, it doesn't keep it in the memory. It loads it and when you need it. All right. So when I run this code now, here, this is going to take a lot less than a minute. It's still not the fastest thing on earth, right? But as you can see, it runs a lot faster, and it gives me some result. It tells me like how to learn to play a piano and whatnot. Now, if I do this Llama PS again, you will see that now I have Llama 3.2 loaded in memory. It's going to stay there for a while, and then if I don't use it, it's going to shut it down. So that is another way to talk to LLMs with Llama, right? Now, what we've been doing so far is you saw two things. One was we put stuff in database, do some embedding, search stuff, and get the stuff, right? The other is we're talking with an LLM. LLM produces some nice response, but these two are like separate worlds. Like, what if you want to use both? So I want the LLM to be able to tell me what books we have in the database, right? Well, first of all, let's consider something here that's called a service. That's something that provides, as I said, like LangChain4J gives you a lot of abstractions that are that makes things very easier. One of those abstractions is a service, and basically that's the same thing. So here I say I have a chat language model, the same thing. It's a llama, except this it uses llama 3.2 model, and I also have an AI service which I called librarian. Right, and it uses that particular chat language model, that one that I created here. And now instead of talking to the model directly, I'm talking to that librarian. Now, why this abstraction? Because when you have and this is the librarian as defined here. So when you have this abstraction, what you can do is you can provide, one of the things you can do is you can provide system messages. So you can send now instructions to your LLM how to behave. And in this particular case, my instruction is your helpful librarian, respond with the names of the books that we have, blah, blah, blah. So let me run this. No, it still runs the previous one. Sorry, current file. This one. So this is going to call the LLM. And it's going to follow the instruction, and as I asked, it's going to give me the 3 books that it knows of, except none of these books is in our database, because this is all the model knows from its training, right? So it figures out, like, if I run this again, it's probably come up and hallucinate 3 more books, right? So it has no idea about the actual books that we have in our database. So we can fix that using an approach that is known as RAG, or Retrieval Augmented Generation. So essentially what we do here is we combine the 2 approaches. We get a query that asks about something, we tokenize it, we vectorize it, and we go and ask the database what is the relevant information for that query. Now, we get from the vector database the relevant information, and then we go and talk to the LLM and say, hey, LLM, give me answer to that question. Oh, and by the way, here is the context for you that we just grabbed from the database. That approach is known as RAG, Retrieval Augmented Generation, and it's somewhat cumbersome to do. It's not rocket science, but it's step-by-step repeatable. So LangChain4J created a very nice way of doing this. So first of all, it's here is again using a model. So this time I'm going to use Gamma 3 through Ollama. Right. Then I'm going to say I'm also going to be using an embedding store or vector database. I'm going to be using Pinecone for this particular one. And then I have this thing called content retriever. Now, as you can see, content retrieval has embedding store. That's going to be using my Pinecone store, and embedding model. And that is the thing that actually gets the results from the database. And here I say I want max 5 results. Right? Now I have something that's called content injector. And then content injector basically says which part of the metadata I want to get. And in this particular case, I'm interested in getting the title. And finally, I have this retrieval augmenter who basically says where to retrieve it from and how to augment it. And so use the content retriever and the content injector to kind of make that query. And that's it. The final thing is the librarian that you saw before, except here it has a little more precise system message, like how to behave. And so if I run this now, you'll see that is exactly what's happening. It goes, grabs the relevant information from the vector databases, and the LLM now responds with, we have Newsies, we have music with the brain in mind. You saw those books before, and Chopin, the Man and His Music. So now the LLM responds with an information that's accurate. That is the actual books that we have in our database, right? Because we were able to pass it, to pass that information to it by retrieving the data from the vector database first, and then pass it to it. So there are tons of other things you can do with LangChain4J. By the way, yesterday they released 1.0, I believe, version. If you want to play with inference side of AI with Java, it's probably a good thing to look at. And it can use behind the scenes lots of other things like Onyx runtime that can run models, but also JLlama, Llama, tons of other things. It also has convenient abstractions for other things like image models or document loaders. So if you want, for example, to scan a folder of PDFs and convert them into embeddings and things like that, you can do this a lot more conveniently with LangChain4J. And it has a memory. And now the memory concept is if you chat with ChatGPT and use any of those tools, you know how it remembers things, right? So if you say my name is, and 3 messages later you say what's my name, it's going to respond your name is, right? Well, that's not the language model. The language model does not remember anything. So ChatGPT is basically 2 parts. It's chat and GPT. And GPT is the model, and it doesn't remember anything. Chat is the application that allows you to talk to the model, and that application is what remembers things, right? And to remember things, you need this concept of a memory. So essentially, with every next request to the LLM, you send the entire history of the conversation, right? And so now that is limited to what is known as context window, because there is only so much data that you can send to the LLM and whatnot. But anyway, the reason I'm telling you all this is because LangChain4J allows you to also use things like that. And last but not least is tooling. Now, before MCP servers, which are a relatively new thing that came up, started by Anthropic last year, and now it's the de facto standard for tooling, there was a way for each LLM to be provided with an information about a tool. So basically, and even you can try this on your own. You can go to ChatGPT and ask it a math question. And what you will see in the bottom right, it's going to tell you that this was calculated by a Python script, and there is a place where you can click and actually see the Python script it generated to calculate, to solve the math equation, right? So this is how LLMs solve things that they don't know how to solve otherwise, by tools. So you have that in LangChain4J as well. So that's pretty much it. I was trying to build up a mental model of those concepts. So you're not going to build the Terminator. You're not going to, solve the biggest enterprise AI problems getting out of this room. But hopefully it gave you an idea of what is what, where to look. As I said, the talk is very, very basic. Hope it was useful. If you want to dive deeper into the AI world from training side and in Java, you may want to have a look at Deep Java Library. These folks are much more deeper into the topic, but that requires a lot of math. Warn you. Feel warned. And that's it. Thanks for having me. Thank you. I hope it was useful. Thank you.